In this video, I'm going to show you how to generate single-use Bitcoin wallets using the Go programming language. You can use this method in a payment processing system, for example, to sell products or services on a website, or you could use it to build a point-of-sale system. Start by creating a directory. I'm going to call my directory Michi, which is the Japanese word for road, and this is an homage to a certain e-commerce website which was an early adopter of Bitcoin. I'm not going to name it in this video. And then in this directory, I'm going to initialize a Go module using go mod init github.com/moros/michi. And in this case, Moros is my GitHub username, and it's also my last name. And then I'm going to initialize a Git repository, stage everything for commit, and then I'm going to create an initial commit using git commit, like so. Now I'm going to create a new directory called cmd/seed, and I'm going to cd into this directory, create a file called main.go, and open this file in a code editor. And next I'm going to define package main and function main. And the first thing we're going to have to do is we're going to have to generate a seed. Now this seed is going to be the basis of all keys we're going to generate in this video. So I'm going to say var seed equals make byte slice with a size of 32. And then using run.read, I'm going to fill this binary with cryptographically secure random bytes. And then in order to check if this seed is correctly generated, I'm going to print this as base 64 to the terminal. Encode to string seed, like so. In a new terminal, I'm going to run go run dot, and we should get a random binary serialized as base 64. Now, if I run this command again, we're getting a different secret, and for now that's okay. Now, obviously in a real world application, you should take very good care of this seed, because this seed is the basis of all of your wallets, and anybody who takes hold of this value can basically steal your funds. So you have to be very careful with it, and I'm going to cover ways to store this seed in the next video. And now, based on this seed, we're going to generate some private keys and wallets. And for that, we're going to need a library. I'm going to install it using go get github.com/btc suite/btcd/btc util/hd keychain. This is a very long path, but this is basically a special package called hd keychain, and it is responsible for generating hierarchical deterministic wallets, and I'm going to show you what this means in a moment. So inside the program, I'm going to create a new master key from the seed, hd keychain new master. We pass the seed and the parameters for mainnet. This is a variable that basically tells the library how to generate, what to generate. And in here we are passing the parameters for mainnet because we want to generate addresses for Bitcoin mainnet. And if you are building a website and you're still in testing, you could use something like testnet or regression test. And there are different variables for it. I think there's a regression net params and there is a testnet free params. For now, let's just use mainnet. If there was an error, and for some reason this seed is unusable, we log the error and exit. And otherwise, we can print this master key to the terminal. So go run, and we get a private key like so. And I'm going to copy this key and I'm going to paste it here. And this is a website called byteapps.com/bip32. And it's called bip32 because the key derivation we are going to do were defined in a document called BIP32, and that's short for Bitcoin Improvement Proposal 32, Hierarchical Deterministic Wallets. And this document defines ways to derive basically unlimited numbers, like practically unlimited numbers of wallets and private keys and public keys from a specific private key. And you can derive private keys or public keys from a private key, and you can derive public keys from just the public key. And what this means is that you can generate addresses on the server, and you only need to store a public key on the server, which means the private key can be securely stored on your development machine or somewhere else. And this means that even if somebody hacks your website, they are not going to be able to steal your coins, because they are going to be protected by your private keys. And this document defines a specific way these wallets can be derived. I think it's somewhere here. And there is even a convention called, there are conventions specified in different documents, and one most commonly used these days is called BIP84. And these are, and by convention, this is a derivation that gives you wallets in, these wallets are going to be used for the so-called segregated witness addresses. And what this means is that you can send I'm not going to go into too much detail about what this segregated witness actually means, but these are like the most commonly used public keys these days. And okay, so these are okay. And now okay, and these are this is what is called a derivation path. And what this means is every segment of this string is an index. So, and M means a master. And this is what is this is a so-called hardened derivation, which means that this key is derived with the parent's private key. And this way you cannot simply guess the parent's private key by looking at the public key, and this is a security measure. And there are 3 levels of hardened derivations, one with the index of 84, one with the index of 0, and one with the index of 0. And then from this last hardened derivation there is a non-hardened derivation, and non-hardened derivations are keys derived from these are keys derived from public keys. And in the next step we're going to try and derive a key like this with the derivation path of 84000 using Go. So to this end I'm going to write a function called derive key, and it's going to take the base key, which is of type HD keychain extended key, and then we're going to take the path, which is going to be an array of uint32, and we're going to return a key, which is going to be of type HDKeychain extended key, and error, which is going to be an error. And first I'm going to assign the base key to this key variable, and then we iterate over all those indices in the derivation path, and then we can say key and error equals, and make sure to use the actual equals operator and not colon equals, because we are assigning to existing variables. And then key dot derive index, if error is not nil, return. And then at the end of this function we return. So next thing we are going to do, so we have a master's private key, and then we want to derive a key called a key with the path. Okay, this is master, and then we want a hardened derivation. A hardened derivation is indicated by the fact that the first byte is going to be the first bit in this integer is going to be 1, and that's what basically just means we have to add this value to the index. That's plus 84, and then the same thing but without this 84, and then the same thing again, and then 0. If there was an error, we basically terminate the program, and then let's try and print this these keys, private key. Oh no, you know what? Let's print this these keys actual elliptic curve public key, and this is going to be the value that's actually going to be used to generate addresses. So pub key error equals derive ec public key. If error is not nil, log fatal error, like so. And then we can print this public key serialized compressed. And by the way, this is going to be a binary, so we have to print it using printf, like so. So now if I run this program, we are getting 3 outputs. We're getting a binary seed serialized as base 64. We're getting the master's private key in this specific format, and then we're getting a derived public key serialized in this way. And maybe we could also try and print this derived public key, like so. Can we not do it? Okay, yeah, sorry, this should be called derived, not derive, like so. Okay, and then we go run it, we're getting 2 private keys, and if we copy this private key and paste it here, we're going to see that it is derived 4 levels deep, and this program cannot really tell how deeply derived it was, but we can actually we can generate addresses based on these derivations. And if we just not do this, okay, this is 1 derivation level too deep. We want to go, we want to get rid of this derivation level, like so. So I'm going to copy this and paste it here, and I want to specify a derivation path like so. So now Okay, like this. So this is a okay, I want to specify a different derivation path, but this program won't let me do it. Wait, again. Let's paste this. Okay. I'm going to paste this key. It is derived 3 levels deep. And so, okay, this is okay. This is not the same key we are expecting, because this is derived 1 level too little. So instead, I'm going to derive it 1 level more. Error equals derive 0, like so. And then I'm going to and then this way this derived key should be at the proper level. So I know this is kind of complicated, but please bear with me. We take this string, or we take this string, like so, and we're going to paste it here. This is the master key, and then we specify a derivation path at 84 prime, which means a hardened derivation, 0 prime and 0 prime. And then if we specify an address type of pay to witness public key hash, we're going to get this address, and this addresses public key is the same as the one we generated in this program, which means that at least this derivation is going the way our implementations expect it to work. So the next thing I'm going to do is I'm going to generate an address, and I'm going to generate an address of the same type as we generated in here, which is P2WPKH, which means, I think it means pay to witness public key hash. And the way this works is I'm going to define a variable called witness prog. I think it just means witness program. And I'm going to generate a hash using this helper method called hash 160. And this is the way this works. It's basically a hash of a hash. It's using 2 different algorithms for the same on the same value. And then I'm going to pass this compressed public key, and then I'm going to generate an address using BTC util new address witness public key hash, like so. So I'm going to pass this witness program and the parameters for the Bitcoin mainnet, and then if there was an error, we abort. And then if there was no error, we can print fmt-println addr encode address, like so. So now I'm going to rerun this program, and now we're getting a bunch of completely unrelated strings. This is the master's seed, this is the master's public key, this is a derived, this is the private key of this key's parent, and this is the address we're going to get generated. So if I take this string and once again paste it on this website, then specify a custom derivation path of 84 prime, 0 prime, 0 prime. If we scroll down and select pay to witness public key hash, we're going to get the same wallet address as here. See, it ends with 9PAXU3, and since the last 6 characters of this address are a checksum, if these characters match, then it's basically almost certain that this is going to match. And then the public key, the one specified here, ends with F1BE48. So this means that at least now we know how to derive keys. And the next thing I want to do is I'm going to specify, actually we're going to persist these secrets, and we're going to write a completely new program. And I'm going to basically write this in this program. I'm going to the only things I'm going to do is we're going to generate a seed. We're going to encode it as base 64 and print it to a terminal. And then we're going to derive a hardened key. And based on that hardened key, we are going to write a different program, which is going to generate actual private and public key pairs for specific payments. And since we are no longer bound by this protocol, we can specify our own derivation paths. And since this is my protocol, I'm going to use 69 because it's nice. And this is also going to kind of throw some hackers off our trail, because this is not a standard wallet derivation path. Also, we're not going to need this master string anymore. And then we're going to need this derived string, except that we are not going to use this private key. We're going to use just its public key. And I'm going to run derived error equals derived neuter. And this neuter function, it removes the private key from this key, and it's called neuter, which in like actual medical speech should mean that it cannot have any children, but actually this is a lie, because this derived key can still have children. And we're going to log and abort if there was an error, like so. And then we are going to print this derived key to the terminal. And then anything that happened below here, we can just delete it for now. This, how does this work? This public key, it was, okay, I'm going to delete all of this for now. And if we run this program now, we are only getting the master seed encoded as base 64, and we're getting a public key derived like so. So if I paste it, copy and paste it in on this website, we can now see that this is a derived key. It derived with a depth of 3, and there is a fingerprint of its parent keeper, and we can see that the derivation path of its parent is 0, like so. And there are some derived keys, but we are not going to worry about this for now. So instead, what I'm going to do is we are going to print this to the terminal, and we're going to use these as templates for environment variables. So I'm going to say printf instead of println, and then I'm going to specify export master seed equals double quote %s. Wait, Why is it? Okay, I think printf backtick export master seed equals double quote %s, and then since we cannot use \n in this inside backticks, we have to specify like this. So this is going to be a shell script. This is going to generate a shell script which is going to which we're going to use to store these values, and then in here we can do a similar thing, fmt printf export public neutered base key equals %s, like so. Wait, plus a new line, and this is going to be derived string. Okay, so now if we run this program again, we're getting this shell script, and I'm going to output it to a file called .drenv in the parent directory of this directory. No, it's called envrc, like so. And since I have a program called drenv, if I create a file called envrc, it's going to be recognized by drenv. And now if I run drenv allow, we're going to get two new environment variables, and these are the same environment variables that we have defined in this script. So I can check this using echo neuter base key, and we are getting a public key. And I'm going to delete this .drenv file because it was mistakenly generated, and we can add a documentation string. So generates a master seed 32 bytes and a neutered extended key with the derivation path of master /69 prime /0 prime /0 prime /0 prime. Outputs both as a shell script template for use with drenv, like so. So now I'm also going to add this envrc file to gitignore. Sorry, I'm going to have to move it to two levels up, and this way, if we add this program to for commit, this envrc file is going to be ignored. Okay, so I'm going to add all changes for commit, and I'm going to commit saying generate master seed and neutered key. And now I'm going to go one level up, and I'm going to create a new directory, and I'm going to call it addresses, and I'm going to cd into this directory, create a new file called main.co, and open it in the code editor, and package main, and so in let's say you're building in a payment system. What's usually going to happen is you're going to get a bunch of orders or payments, and these payments can be, there can be a multitude of payments, and then depending on the type of your private keys, of your primary keys in the database, you're going to either get integers or you're going to get UUIDs. And I'm going to go along with this project just assuming you're using UUIDs, but you can also find out ways to do something similar even if you are using integers. You'll just have to serialize your integers as binaries. And I'm going to generate a few UUIDs using Ruby because this is like the fastest way to do it quickly. So I'm going to take this UUID and going to copy it to the program. So var order IDs, it's going to be a slice of strings, like so. We have one, and I'm going to generate a few so I can show you how this can work on a larger scale. This is not very efficient, but it's good enough, I guess. Okay, missing a line. Okay, so we have 3 UIDs, and I'm going to define a function main, and I'm going to define a helper function called mustGetEnv, and it's going to take a string key and it's going to return a string. And what this is going to do is we're going to read the value from the environment process, from the process's environment variables, and if the value is an empty string, we're going to print a message on a board. Fatal environment variable with this name is not defined, and print the key, and otherwise we return the value. So what's going to happen is you're going to need the master seed. Oh, you know what? Actually, we don't even need a master seed in here. We just need the neutered public key. Wait, what was it actually? Cat LVRC. Okay, it's called neuter base key equals mustGetEnv neutered base key, and then okay, and then we're going to have to parse this base key using key error equals hd keychain new key from string neutered base key, like so. If there was an error, we abort, and otherwise we can print we can just, for now we can just print a public key or something, or fmt println base key. What do we have? We can print yeah, let's just print the depth so we can prove that we are actually parsing this this key. So if I run go run, we get the depth of 3, which means that we have successfully read this key from the environment and that we have parsed it as an extended key. And then what I'm going to do is I'm going to take the function called derive key from this program, and I'm going to copy and paste it in this file. Yep. And the reason I'm going to do this is because we are going to use it with we're going to use it in a similar way to the previous program. And okay, I'm going to remove this debugger statement. And the way you can derive key pairs based on the order's UID is, first, you're going to have to parse this. You're going to have to parse this UID as a binary, and we have them in hex format. So I'm going to remove okay, I'm going to take this first one of these orders. I'm going to remove the dashes, and I'm going to parse it as hex. And in order for this to compile, I'm going to just ignore this variable, and let's print this. Let's just print this parsed UID like so. Go run dot. So this looks almost the same as the original UID, because UIDs are already hex encoded. And then I'm going to use a hash function to derive two numbers from this UID. But I'm not going to use any hash function. I'm going to use an HMAC. And in order to use an HMAC, we're going to need a key. So I'm going to generate a key. OpenSSL-rand OpenSSL-rand-base 6464. It's going to be 64 bytes long, and I'm going to remove all new lines, and this is going to be our key, and I'm going to copy it to the system clipboard. This is a Linuxism. You can use pbcopy on macOS. And I'm going to open this .envrc file, and I'm going to say export HMAC. You know what? I'm just going to call it secret keybase. I'm going to call this variable secret keybase, and then we're going to use it to derive more values. So if I remember correctly, for HMAC SHA-256 key length, the key should be 32 bytes long. Yeah, so this is basically just going to be a trick, but Golang Xcrypto Argon 2. We are going to derive a key from this secret keybase, and okay, so I'm going to install this library, and I'm going to once again run drenv allow to allow this secret keybase to be parsed, and I'm going to write a new function called must get env base 64, and it's going to take a key which is a string, and it's going to return a binary, and the value is going to be must get env key, and then bytes error equals base 64 standard encoding equals string value. If there was an error, we say fatal F, fatal failed to decode environment variable from base 64, and this is going to be key, and then we return the bytes, and then the secret key base equals must get end base 64 secret key base. So now if we cd into address and go run dot, nothing changes, but at least it compiles and does not complain. Okay, and then I'm going to use argon2id to derive a key. So I'm going to say hmac key equals argon2 id key, and this takes, it first takes a password, which in this case is going to be secret key base, and then it takes a salt, and this salt is going to be let's just call it I'm just going to call it derivation path, like so. And then we have to specify the arguments for this function. I'm going to pass time is going to be 2, and then 64 megabytes of RAM, and parallelism of 1, and we want a key length of 32. So let's see if we can derive it like so. Okay, it worked. So now we I'm also going to print this hmac key for debugging, just to see that it's derived, and it's derived the same way every time. Okay, this is our hmac key, this is our UID. And what I'm going to do, okay, no, this is the wrong program. What I'm going to do is I'm going to write a helper function called I'm going to call it derivation path from order ID, and it's going to take an order ID as a binary, and it's going to return 2 segments, and they are going to both be uint32 and uint32. And I'm going to perform an hmac. So I think it's like, we can call it sum equals hmac new, and it's going to take SHA-256.new, and the key is going to be hmac key, and then I think that was the way you do hmac in. Yep, and sum write order ID, and then return sum.sum and with nil. No, wait. So this is going to be, I'm going to rename this variable to mac. I'm going to rename this to mac, and the sum is going to equal mac.sum. And then I'm going to take the first 4 bytes of this value and the last 4 bytes of this value. So if I remember correctly, this hmac is going to be 256 bits long, which is 32 bytes. So I'm going to define another function called uint32 derivation index from bytes. And it's going to take a bytes, which is going to be a byte slice, and it's going to return a uint32. And we're going to define a variable called val, which is uint32, and then we need to call binary.decode bytes, and then you have to pass an endianness. I'm going to use little endian because it is native for most modern architectures, and it's going to put this value into val, and then I'm going to return this value, but I'm going to truncate the first byte. So I'm going to sum it with 0x7 ff, 7f, ff, ff, and ff, like so. And this way we can be sure that the first bit is going to be 0. So now I'm going to say return derivation index from bytes, and I'm going to pass the first 4 bytes, and I'm going to pass the last 4 bytes, like so. Derivation index from bytes. Okay, so we're going to return two integers, and I can remove this index for now, remove this key for now. So yeah, I think this is too descriptive. I'm going to call it bytes to index, like so. So and I'm going to call this order ID to path. Okay, so let's run this function. Segment1, segment2 equals order ID to path UID, and then you can print segment1 and segment2, like so. So now we're getting two integers, and we can see that every time we run this function, this program, we're getting the same values. So let's try it with the other order IDs. For ID equals range order IDs. We can run the same for the other remaining IDs, and if error is not nil, log fatal error. And if you run this program again, you can see that we are parsing all order IDs that we have defined in this original array, and that we are getting two integers for each order ID. And we can also make sure that all of these are less than this hardened derivation threshold, because we cannot derive hardened keys from just the public key. And then you know what, actually we could improve this function even more. So I can just return it like this. So var result, it's going to be make a slice of uint32s with the size of bytes, and like so, wait, no, and for index and binary in the range of bytes, we can decode, we can decode this binary, and then okay, I'm going to rename this as slices, and then I'm going to rename this as slices, and then this is going to be slices as well, and then I have to rename this as slice, and this as slice, and I'm going to pass store this in the variable results. I equal results, this equals this new value, and then we can return the results. So then instead of calling this function twice, we can just call it with a variadic arguments. So I can just make it return a slice, and this way we can just call it later as we can just get a path like this. So let's compile this again. So you can see what we are getting a slice instead of two variables, and then we can use this to derive keys. So derived key equals base derived key base key with a path. If there was an error, we say log we abort the program, and then we can fmt printf. We can print this derivation path. It's going to be M69 prime 0 prime 0 prime, and then slash this and slash this, and it's going to be path 0 path of 1, and then the derived public key is going to be public key error equals derived EC pub key. If there was no error, we abort the program, and then we can okay, and I'm going to add some labels. So order ID is this, and I'm going to print ln at the end of this loop, and then you can say fmt printf. Okay, and also here I'm going to add a new line. So a public key is this, and we can print this as a string. Wait, okay, I can only print it as serialized compressed, and then this is going to be a hex. So if I run this program, you can see that based on this UID, we're getting this derivation path and this public key, and then based on this serialized key, we can then build a witness program, and it's going to be btc-util hash 160, and we're going to just hash this serialized and compressed key, and then we generate an address equals btc-util new address witness public key hash, witness program, and then mainnet params. And then if there was an error, we abort. And then if there was no error, we print this address, like so. So now we are getting this, so now we have this custom derivation path. It's going to be kind of difficult to ensure that these are actually valid, but in another video we can, when we actually try to sweep these wallets, we can also derive private keys from the seed, and then we can make sure that these private keys actually match these public keys. So this was a video on generating wallets, and I know this way is kind of idiosyncratic, and I kind of came up with it on my own with some help from my friend ChatGPT, and I think it could work. And actually, when you have this public key and you have this address, you can ask a Bitcoin node to send you notifications whenever a transaction arrives at this address. So the way you would store it in a database is you don't even have to store the whole address, because even this address can kind of identify you. So what I would store instead is I would also store an HMAC of this address in the database, and then when a transaction arrives and it says it arrived to this address, then we can be sure that we can then just check this, and we can HMAC the address of the arriving transaction, and then we can find the order in the database based on that HMAC. And also I wouldn't store anything else besides this, like as long as the order ID does not change and we don't change the secret key base and this HMAC key, then this derivation path is going to remain constant, and this should be enough to derive the private key and sweep coins from this address. And also, since we are using a custom derivation path, even if somebody steals your seed phrase, your master seed, you're going to have a very hard time looking for coins at addresses that are derived with such big indices. Like most wallet software only searches the first 20 addresses on one derivation path, because for every address you have to scan the blockchain to see if there were any transactions. And if they have 4 billion times 4 billion, which I think is 16 quadrillion, I'm not sure if anybody is going to scan 16 quadrillion addresses. But that also means that you really need to hold on to all of your transaction records, because if you lose this address, you will probably never find it again. Okay, if you're new to this channel, my name is Karol Moroz. My channel is called Make Programming Fun Again, and this was my first video about Bitcoin and the blockchain. And I dedicated to a 16-year-old myself, who was supposed to, be an early blockchain adopter in 2009, but I was stupid and I did not learn Bitcoin back then. So now I have to make these videos. If you enjoyed this video and you would like to see more, please like and subscribe. I hope you learned something, and I will see you in the next video. Thank you.